Welcome to today's problem walkthrough. In this session, we will be tackling LeetCode problem number 21, merge two sorted lists. This is a fundamental problem that helps build a strong understanding of linked lists and iterative or recursive problem solving. Let's dive in and explore different approaches to solve this problem effectively. In this problem, you are given the heads of two singly linked lists, named List 1 and List 2. Both of these lists are already sorted in non-decreasing order. The goal is to merge these two lists into a single linked list that is also sorted in non-decreasing order. The merging process involves splicing together the nodes of the two input lists, rather than creating new nodes. Once the lists are merged, the function should return the head of this new sorted linked list. For input, you'll receive the heads of the two linked lists, and the output will be the head of the merged and sorted list. Let's look at some examples to clarify this further. Consider the first example where list 1 is 1, 2, 4, and list 2 is 1, 3, 4. The output in this case is 1, 1, 2, 3, 4, 4. Here's how this result is achieved. Since both input lists are already sorted, you compare the first elements of each list. The values won from both lists are equal, so the first one is added to the merged list. Then, you move to the next node in list 1 and compare 2 with the one in list 2. Since 1 is smaller, it's added next. This process continues, comparing and merging nodes one by one. By the end, all elements are in sorted order in a single list. Now, if both input lists are empty, as shown in the second example, the output is simply an empty list, since there are no nodes to merge. In the third example, list 1 is empty, and list 2 contains a single node with the value 0. Since the first list has no nodes, the merged list is just a copy of list 2, resulting in 0. This demonstrates that if one list is empty, the merged list will directly be the non-empty list. Moving on, there are some constraints to consider. Both lists can contain up to 50 nodes, and the value of each node will fall within the range of -100 to 100. Lastly, it's important to note that both input lists are guaranteed to be sorted in non-decreasing order, which makes the merging process straightforward. When solving this problem, you should also account for a few edge cases. For instance, if one or both of the input lists are empty, the result is simply the non-empty list or an empty list if both are empty. Another edge case is when all nodes in both lists have the same value. In that scenario, the nodes are merged in sequence, preserving the order. When the input lists have unequal lengths, such as list 1 being longer than list 2, the merging process should still handle all elements correctly. Lastly, the solution must handle negative values seamlessly, ensuring the merged list remains sorted. Remember, the merged list should be constructed by reusing and rearranging the original nodes without creating new ones. Additionally, the solution should aim for an efficient time complexity of O, n plus m, where n and m are the lengths of the two lists. To tackle the problem of merging two sorted linked lists, let's start with a brute force approach. The intuition here is straightforward. We create a new linked list and iteratively compare the nodes of the two input lists. At each step, we append the smaller of the two nodes to our new list and move the pointer forward for the list from which the smaller node was taken. Once one of the lists is fully traversed, we simply append the remaining nodes of the other list, since it's already sorted. This ensures that the final merged list is also sorted. This process involves using two pointers to traverse both lists, comparing their current nodes, and appending the smaller one. The time complexity of this approach is O, m plus n, where m and n are the lengths of the two lists, since we visit each node exactly once. The space complexity is O, 1, because we don't allocate additional memory apart from the output list. As for trade-offs, this method is efficient and simple for small to medium-sized lists. However, it modifies the input lists directly, which might not always be desirable in certain scenarios. Now, let's consider an optimized approach using recursion. This method is cleaner and more elegant, leveraging the natural structure of recursion to simplify the merging process. The key idea is to compare the heads of the two lists recursively. At each step, we attach the smaller of the two nodes to the result of merging the remaining nodes from both lists. The base case for this recursion is when either list becomes empty. In that case, we return the other list as it is, since it's already sorted. This process continues until both lists are fully traversed. In terms of complexity, the time complexity remains O, m plus n, as every node is visited exactly once. However, the space complexity increases to O, m plus n, due to the recursive function calls that occupy the stack. While this approach is highly readable and concise, it comes with a significant trade-off: the risk of stack overflow when dealing with very large lists due to the depth of recursion. This makes it less suitable for input sizes that could potentially exceed the stack limit. Merging two sorted lists efficiently relies on a key observation: since the input lists are already sorted, we can directly merge them in linear time without any need for additional sorting operations. Both iterative and recursive approaches yield the same time complexity of O, m plus n, but they differ in terms of space usage and code clarity. After evaluating these factors, we chose the iterative approach for its balance of simplicity, efficiency, and robustness. Unlike the recursive approach, which is elegant and concise but risks stack overflow for very large inputs, the iterative method avoids recursion depth issues entirely. By directly manipulating pointers in a loop, the iterative approach ensures constant space usage, making it more suitable for production-scale inputs. When compared to a brute force approach, the optimized methods stand out due to their ability to directly modify pointers without unnecessary copying or restructuring of nodes, which reduces overhead and enhances performance. In conclusion, the iterative solution provides the best trade-off between clarity, efficiency, and scalability, making it the ideal choice for this problem. To solve the problem of merging two sorted singly linked lists into one sorted linked list, we first need to understand the input and output. The input consists of two linked lists, list 1 and list 2, where each list is already sorted in ascending order. The goal is to create a new linked list that merges the nodes from these two lists while maintaining the sorted order. Instead of creating entirely new nodes, we will splice together the existing nodes from list 1 and list 2. The output will be the head of this new merged linked list. To simplify the merging process, we use a dummy node, which acts as a placeholder at the start of our new list. This dummy node helps eliminate edge cases, such as when one or both input lists are empty. We also use a pointer called current, which initially points to the dummy node. This pointer allows us to track the position where the next node should be appended in the merged list. With the dummy node and current pointer set up, we now traverse both input lists simultaneously using a while loop. This loop continues as long as neither list 1 nor list 2 is exhausted. During each iteration, we compare the values of the current nodes in list 1 and list 2. If the value in list 1 is smaller or equal, we append this node to the merged list by setting current dot next to the node from list 1. Then, we move the pointer in list 1 to its next node. Otherwise, we append the node from list 2 and move its pointer forward. After appending a node, we advance the current pointer to the newly added node in the merged list. Once one of the lists is fully traversed, the loop ends. At this point, the other list may still have remaining nodes. These nodes are already sorted, so we can append them directly to the merged list by setting current dot next to the remaining nodes. Finally, the merged list starts from dummy dot next, as the dummy node itself is just a placeholder. We return this node to complete the algorithm. There are several key insights that make this algorithm efficient and elegant. First, the use of a dummy node simplifies the construction of the merged list. It allows us to avoid special handling for the initial nodes, ensuring that we always have a reference to the head of the merged list. Second, we optimize memory usage by reusing the existing nodes from list 1 and list 2 instead of creating new ones. This in-place reuse of nodes ensures that the algorithm remains space efficient. In terms of time complexity, the algorithm is highly efficient because it iterates through all nodes in list 1 and list 2 exactly once. If the lengths of the two lists are n and m, the time complexity is O, n plus m. Space complexity is O, 1, since we only use pointers to traverse and manipulate the lists, without allocating additional memory for new nodes. The algorithm relies on a few core data structures. Each node in list 1 and list 2 contains a value and a pointer to the next node. The dummy node is a temporary node used to simplify operations on the merged list, and the current pointer tracks the tail of the merged list as we build it. Additionally, we use pointers to traverse the input lists. It's also important to consider edge cases. If one or both lists are empty, the algorithm handles this naturally by returning the non-empty list directly, or null if both are empty. When the lists have different lengths, the remaining nodes from the longer list are appended after the traversal loop. Finally, duplicate values are preserved and merged in sorted order, as the algorithm always compares nodes sequentially and appends them appropriately. To solidify our understanding, let's walk through an example. Suppose list 1 contains the nodes 1, 3, and 5, while list 2 contains the nodes 2, 4, and 6. First, we initialize the dummy node and the current pointer. We then compare the first nodes of list 1 and list 2. Since 1 is smaller than 2, we append the node with value 1 to the merged list and move the pointer in list 1 forward. Next, we compare 3 from list 1 with 2 from list 2. This time, 2 is smaller, so we append it to the merged list and advance the pointer in list 2. We continue this process, comparing and appending nodes in sorted order, 3, 4, 5, and finally 6. Once all nodes are processed, the merged list is complete. The final result is a single sorted list, 1-2-3-4-5-6, which we return starting from dummy.next. Here, we start by defining a class called listNode, which represents a node in a singly linked list. Each node has two attributes, val, which stores the value of the node, and next, which points to the next node in the list. Next, we define a solution class that contains the method mergeToLists. This method takes two sorted linked lists, list 1 and list 2, and merges them into one sorted linked list. To begin, we create a dummy list node, which acts as a placeholder for the start of the merged list. We also create a variable called current that initially points to the dummy node. This current pointer will help us build the merged list step by step. Then, we enter a while loop that runs as long as both list 1 and list 2 are not empty. Inside the loop, we compare the values at the current nodes of list 1 and list 2. If the value in list 1 is smaller or equal, we link the current node to list 1, and move list 1 to its next node. Otherwise, we link current to list 2 and advance list 2 to its next node. After making the connection, we move the current pointer forward to continue building the merged list. Once the while loop ends, it means one of the lists has been fully traversed. At this point, we check if there are any remaining nodes in list 1 or list 2. If list 1 still has nodes, we directly append them to the merged list by setting current.next to list 1. Similarly, if list 2 has remaining nodes, we append those to the merged list by setting current.next to list 2. This ensures that all nodes from both lists are included in the final merged list. Finally, since the dummy node was just a placeholder, the actual merged list starts from the node after dummy. We return dummy.next as the head of the merged list, completing the implementation. This approach ensures that the merge process is efficient and maintains the sorted order of the lists. Here, we start by defining a class called listNode, which represents the structure of a node in a singly linked list. Each node has an integer value, val, and a reference to the next node, next. We provide three constructors, a default constructor, one that initializes the node with a value, and another that initializes it with both a value and a reference to the next node. Below that, we define the solution class, which contains the method mergeToLists. This method takes two sorted linked lists, list 1 and list 2, as input and merges them into a single sorted linked list. Inside the method, we first create a dummy node, which acts as a placeholder to simplify the logic of managing the merged list. We also initialize a pointer, current, that will help us build the merged list by always pointing to the last node in the new list. Next, we use a while loop to traverse both input lists as long as neither is empty. During each iteration, we compare the values of the current nodes in list 1 and list 2. If the value in list 1 is smaller or equal, we attach the node to the merged list by setting current.next to list 1. We then advance the pointer in list 1 to its next node by setting list 1 equals list1.next. On the other hand, if the value in list 2 is smaller, we attach the current node from list 2 to the merged list by setting current.next to list 2, and similarly advance the pointer in list 2 to its next node. After attaching the chosen node, we move the current pointer forward in the merged list by setting current equals current.next. Once the while loop ends, it means at least one of the input lists has been fully processed. At this point, we check if there are any remaining nodes in list 1 or list 2. If list 1 is not null, we attach the rest of its nodes to the merged list by setting current.next equals list 1. Otherwise, if list 2 is not null, we do the same for list 2. Finally, since the dummy node was only a placeholder, the actual head of the merged list will be the node after dummy. Therefore, we return dummy.next, which gives us the complete merged and sorted linked list. To solve the problem of merging two sorted linked lists, we start with an example where list 1 contains the elements 1, 2, and 4, and list 2 contains the elements 1, 3, and 4. To facilitate the merging process, we create a dummy node with a value of 0. This dummy node serves as the starting point of our merged list. We also initialize a pointer, current, which points to the dummy node. The merging begins by comparing the first values of each list. Since the value at the head of list 1 is 1, and the value at the head of list 2 is also 1, we attach the node from list 1 to the merged list by setting current.next to list 1. After this, we advance the list 1 pointer to its next node, which now points to the value 2, and move the current pointer to the newly added node, which has the value 1. This sets up the initial structure of the merged list as 0, 1. Next, we compare the current values of list 1 and list 2. Now, list 1 is pointing to the value 2, and list 2 is pointing to the value 1. Since 1 is less than 2, we attach the node from list 2 to current.next and advance the list 2 pointer to its next node, which now points to the value 3. The current pointer is updated to the newly added node with the value 1. The merged list now looks like 0, 1, 1. We then compare the values again. With list 1 a 2 and list 2 a 3, 2 is less than or equal to 3, so we attach the node from list 1 to current.next and move list 1 to its next node, which now points to the value 4. The current pointer is updated to the node with the value 2, resulting in the list 0, 1, 1, 2. Continuing, list 1 now points to 4 while list 2 points to 3. Since 3 is less than 4, we attach the node from list 2 to current.next, move list 2 to its next node pointing to 4, and update current to the node with the value 3. The merged list becomes 0, 1, 1, 2, 3. Finally, with both list 1 and list 2 pointing to 4, we attach the node from list 1 to current.next, move list 1 to none, and update current to the node with the value 4. The merged list so far is 0, 1, 1, 2, 3, 4. At this stage, list 1 is exhausted, meaning it has no more nodes. We attach the remaining nodes from list 2, which is just the node with the value 4, to current.next. This completes the merged list, resulting in 0, 1, 1, 2, 3, 4, 4. After removing the dummy node, the final output is 1, 1, 2, 3, 4, 4. Now, let's move to another example. Here, list 1 contains 1, 3, and 5, while list 2 contains 2, 4, and 6. As before, we create a dummy node with a value of 0 and initialize current to point to it. We start by comparing the values at the heads of both lists. Since 1 is less than 2, we attach the node from list 1 to current.next, move list 1 to its next node pointing to 3, and update current to the node with the value 1. The merged list so far is 0, 1. With list 1 pointing to 3 and list 2 pointing to 2, we now compare these values. Since 2 is less than 3, we attach the node from list 2 to current.next, move list 2 to its next node pointing to 4, and update current to the node with the value 2. The merged list becomes 0, 1, 2. Next, with list 1 still at 3 and list 2 at 4, we attach the node from list 1 to current.next, move list 1 to its next node pointing to 5, and update current to the node with the value 3. The merged list is now 0, 1, 2, 3. Continuing, since 4 is less than 5, we attach the node from list 2 to current.next, move list 2 to its next node pointing to 6, and update current to the node with the value 4. The list becomes 0, 1, 2, 3, 4. Finally, we attach the node with the value 5 from list 1 to current.next, move list 1 to none, and update current to the node with the value 5. We then attach the remaining node from list 2, which is 6, to current.next. The complete merged list is 0, 1, 2, 3, 4, 5, 6. After removing the dummy node, the final output is 1, 2, 3, 4, 5, 6. Lastly, let's consider a simpler example where list 1 is empty, and list 2 contains just the value 0. Since list 1 is already exhausted, we directly attach all nodes from list 2 to current.next. This results in the merged list 0, 0. After removing the dummy node, the final merged list is simply 0. This completes the walkthrough of merging two sorted linked lists through different scenarios. The time complexity of the merge two lists function is O, n plus m, where n represents the number of nodes in list 1 and m represents the number of nodes in list 2. This is because the function iterates through both linked lists, comparing their nodes one by one. During each iteration, a single node is appended to the merged list, and either list 1 or list 2 is advanced. Since each node from both lists is processed exactly once, the total number of iterations is proportional to the combined number of nodes, which is n plus m. At the end of the loop, any remaining nodes from the non-exhausted list are directly linked to the merged list. This final operation is done in constant time, O1, since no additional traversal is needed. Therefore, the overall time complexity is O, n plus m. In terms of specific cases, the best case occurs when both lists are empty, meaning n and m are both 0, resulting in a time complexity of O, 0. The average case happens when the nodes of list 1 and list 2 are interleaved, and the time complexity remains O, n plus m. The worst case occurs when one list is fully traversed before the other, such as when list 1 is completely exhausted while list 2 has all remaining nodes. Even in this scenario, the time complexity is still O, n plus m. Now, regarding space complexity, the function operates in O1 space. This is because it uses a constant amount of extra memory for variables like dummy and current. No additional data structures are used to store intermediate results, and the merged list is created by reusing the existing nodes from list 1 and list 2 by adjusting their next pointers. This means no extra memory is allocated for a new list, keeping the overall space complexity at O1. If we compare this approach to a naive solution, the difference becomes clear. A naive method might involve creating a completely new list and copying all nodes from list 1 and list 2 into it. While this approach would still require O, n plus m, time to traverse both lists, it would also need O, n plus m, additional memory to store the new nodes, increasing the space complexity. In contrast, the optimized approach we use directly modifies the next pointers of the existing nodes, avoiding the need for extra memory. As a result, the time complexity remains O, n plus m, but the space complexity is reduced to O1. To validate the time complexity mathematically, consider that each node from both lists is processed exactly once. For every node, we perform constant time operations such as value comparisons and pointer adjustments. The total number of operations is proportional to n plus m, which confirms that t, n, m equals O, n plus m. Meanwhile, the space complexity is constant because no additional memory is allocated, so S, n, m equals O1. When working on merging two sorted linked lists, there are several common pitfalls to watch out for. First, modifying the input lists directly can be problematic. It's tempting to splice nodes from one list into another, but this approach can lead to unintended side effects, especially if the original lists are needed elsewhere in your program. Instead, aim to create a new structure during the merge. Another common issue is overlooking edge cases. For example, what happens if one or both of the lists are empty? Or if the lists contain only a single node? These scenarios are easy to miss and can result in runtime errors or incorrect outputs, so it's crucial to test for them thoroughly. Additionally, inefficient node comparisons can slow down your solution. Repeatedly traversing the lists unnecessarily, such as forgetting to maintain pointers to the current nodes, can increase time complexity. Pointer management itself is another common source of mistakes. Forgetting to update the current pointer or accidentally skipping nodes can lead to infinite loops or incomplete results. Finally, in languages like C++ or Java, it's important to handle memory allocation and deallocation carefully to avoid memory leaks, especially when creating new nodes during the merge process. Now, let's focus on what interviewers typically look for when discussing this problem. It's essential to understand the problem fully. Your goal is to merge two sorted linked lists while maintaining their sorted order and minimizing extra space usage. A clear and efficient solution is key here. Interviewers will often probe how your solution handles edge cases, such as one or both lists being empty, or when the lists have overlapping values. Make sure you're prepared to explain these scenarios in detail. Time and space optimization is another critical aspect. While a brute force approach might be acceptable as a starting point, you're expected to refine it to achieve O(n) time complexity and O(1) extra space by using in-place node manipulation. Additionally, interviewers appreciate when candidates discuss trade-offs. For example, you might compare iterative versus recursive approaches, weighing factors like memory usage, clarity, and efficiency. Being able to justify why you chose a particular method demonstrates a strong understanding of the problem and its constraints. Next, let's explore some related problems that build on similar concepts. One notable example is merge k-sorted lists from LeetCode 23. This is essentially an extension of merging two lists but requires managing multiple sorted linked lists efficiently, often using techniques like a priority queue. Another related problem is sort list from LeetCode 148, where the goal is to sort a linked list by merging smaller sorted sublists, a conceptually similar approach. Reverse nodes in kgroup from LeetCode 25 also ties into this topic, as it involves linked list manipulation, albeit with added complexity like reversing groups of nodes. Lastly, add two numbers from LeetCode 2 is worth mentioning. Although this problem focuses on arithmetic operations, it also requires systematic traversal and manipulation of linked lists. Familiarity with these problems can strengthen your understanding of linked list operations and prepare you for variations in interviews. Finally, let's consider some alternative approaches to this problem. The iterative approach is a common choice. By maintaining two pointers for the input lists and comparing nodes one at a time, you can build the merged list efficiently. This method has an O(n) time complexity and O(1) space complexity, but it requires careful management of pointers to avoid errors. On the other hand, the recursive approach offers a more elegant and concise solution. By comparing nodes and calling the function recursively, you can achieve the same result with simpler code. However, this comes at the cost of O(n) stack space, which can be a concern for very large inputs. A third alternative involves using a priority queue or heap, especially if the problem extends to merging k-sorted lists. The heap allows you to efficiently retrieve the smallest node at each step, making it a generalizable solution. However, this approach introduces extra space complexity, typically O(k), due to the heap structure. Each of these methods has its own trade-offs, and understanding them will help you choose the best approach for different scenarios. Great job making it through the problem. We covered the key aspects of merging two sorted linked lists, including different approaches and their trade-offs. Remember to practice similar problems to solidify your understanding. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!